But one additional hat I have, as a long one, is I'm chair of the Vulkan System Integration Subgroup. Recently renamed from WSI, which is Windows System Integration, which is the main thing we've been working on since the inception of Vulkan. So today I'll be talking about swapchains, which is the meat of Vulkan WSI, and how you create them and how they get used. So let's get going. So a bit of jargon busting to kick off with, because I'll be using these terms throughout the talk. Platform, whenever I refer to a platform, I'm talking about an operating system, Windows system platform. So Android, Windows, Wayland, etc. Not a chipset or anything. A presentation engine is a term we use to describe the platform's compositor or the display engine used in order to get things onto the display, onto the screen. And when I say application, I mean your app, your game engine. It's the thing above the API that's whatever that is, be it a fancy game engine or an app directly using Vulkan. So the great thing that Windows System Integration in Vulkan brings is a similar approach of explicit control to presentation that we do to graphics and other GPU job management. And it's designed, the whole process was designed to fit today's compositing Windows systems and actually look at how what they need from the API as we shaped it. Not all extensions that form Vulkan WSI are supported by every platform. You must check and enable, as Tom said in his talk, any extensions your application uses. So make sure that they're advertised, and you'll discover that some platforms, some extensions are not available. So today's presentation is the basics of actually using all the stuff you've heard so far. Now you want to hit the screen. What do you need to do to get there? So how many WSI extensions are there? 10. I'm not going to go through each one in very detail, you'd be glad to hear. There are 2 cross-platform instance extensions, so that's where Tom described in the loader an extension existing. The Surface extension, which introduces the VK Surface object, and the Display extension, which is about display management, which I'll be explaining later. Then there's 6 platform instance extensions, which they basically hook up your platform native types to the Vulkan surface. They're all fairly light, not for very obvious reasons. And there's 2 cross-platform device extensions. The swapchain extension, which is the bulk of WSI's meat, and the display swapchain, which extends the swapchain extension for going direct to display. Vulkan surfaces are, firstly, not an equivalent of an EGL surface. So they both take you on your route between your window to your buffer or your image that you're rendering to. But unlike an EGL surface, when you create a Vulkan surface, all it does is encapsulate the native type of the platform. It doesn't go off and start creating buffers or anything like that. That's for later, we'll get there in a second. The reason we created the Vulkan surface object is to be able to create platform-independent queries. So once you've abstracted your platform-specific native window handle, native surface handle into a Vulkan surface handle, you can then figure out what format is it, what usage will the images that create from it have, what transform is it currently in, and can it support other transforms, all done in a platform-independent way. Additionally to that, there are also some platform-specific queries, so that we haven't tried to abstract everything across all platforms. We've realized some things are unique to specific platforms. Now, the key thing is presentation support is dependent on a queue family. So each queue family, and I've got like 3 examples of physical devices. you can have multiple queue families in a physical device. Each one may or may not support presentation, and may or may not support presentation to a specific platform. So physical device C in this diagram, there's no presentation. So that could be like a computer-only Vulkan implementation. You can't actually get to the screen. Whereas physical device A has a queue family that can actually hit 2 platforms. And this is an example in the Linux world when you have both Wayland and X living alongside each other on the same implementation. You can have one Vulkan device that actually can support both. So, swap chain, the meat I was talking about. In essence, a swap chain is an array of presentable images. A presentable image is a Vulkan image, a VK image, but the one that you obtain from a swap chain. The application gets to request the minimum number of presentable images. So if you want to be double buffered, triple buffered, or have additional ones for the way your engine works, you can request it. And the implementation creates at least that number subject to a limit. So the memory limits, my recommendation, if you're presenting WQHD, don't allocate 7 depth swap chains because you're going to run out of memory. So be sensible about how you use it, but it gives you that flexibility and choice on patterns that can support it. The cool thing about how swap chains are designed is that the presentable images are allocated up front, so avoiding hitches last minute during your frame loop, and allowing, as Michael described earlier, command buffer content being pre-recorded to fit a specific swap chain image. So you have multiple command buffers to target each one of your images in your swap chain, but you can pre-record them in advance. There's several present modes that we've designed. FIFO is mandatory everywhere, and for those of you that love ETL, woo, yay! There always has to be one. FIFO is like swap interval 1, whereas we finally kind of realized that we disagree what swap interval 0 means on different platforms, so we've divorced the meaning of swap interval into a couple. There's a mailbox mode, which basically means I'll use the latest image, but no tearing, and an immediate mode, which is go straight on to read whatever I've sent to you, and you may end up with some tearing. So that's what we've built. And there's also another mode, which is like swap control tear, FIFO relaxed. Look into the extension for that explanation. It's a bit more cumbersome. So swap chains are good. This joke doesn't work as well here in our esteemed British audience. It's mainly targeted at Tom in the back that calls everything awesome. When he receives an email, it's awesome. I say these are good, which to Americans means awesome. Swap chains are very well designed in terms of how applications need them, and we've had very good feedback overall about how they've been designed. A key thing that we've done is you know which image within the swap chain you'll be presenting, and the content of that image is preserved from the previous content you put on it. So it's similar but not exactly the same as how buffer age and partial update has done it in EGL, but it's done in a way that you don't have to query to find out the age of the image you've obtained. You know it because you're about to send that image in and you know how old it is. The application is also responsible for recreating swap chains, so no surprises, no surprises at all. Sorry, a joke. This is different again from how EGL does things. So in EGL, the platform, after you call swap buffers, can say, oh, by the way, your surface has changed size, just to let you know after the fact, and does scaling or cropping to deal with it. In Vulkan, you, the application, are responsible for dealing with that. You will be notified, and I will go through how that's done in a second. but you need to recreate the swap chain, or you need to deal with that if a resize occurs. It doesn't just happen magically and then lead to some painful orientation changes and resize behavior. Swap chains are jolly good, which means super awesome. The presenting and acquiring operations are separate, as Tobias alluded to in his talk. So there's no need to submit a new image just to acquire the next one you want to work on, depending on what the presentation engine is up to. So I have to add that proviso that if the presentation engine is hogging the images, it may say, actually, you need to release one, you need to submit one into the presentation engine in order for another one to be free. So there are limits to this, but the implementations we're seeing, and most platforms will be able to give you that flexibility that you can acquire separately from presenting. And that's, again, contrasting with how EGL swap buffers works, which is when you call swap buffers, you're both presenting and acquiring at the same time, and that's one operation. And we wanted that to be divorced to avoid stalls in your frame loop, because they're very bad. Very bad. Gone. And the other key point is about ownership. So the presentation engine must only display the images that it has been given. When we get to front buffer rendering, eventually we'll see what happens there. That will be a bit more exciting. So the steps to get your presentable images. So first off, you use your platform-specific code to create your native window, native service, whatnot. You create a Vulkan service from it. You query information using the platform independent queries to figure out what your service can do. You create a swap chain using that information, and from that you obtain your presentable images. And what I'll show you here is how that's divided between the extensions and the platform. So platform-specific, that's left to Android, Windows, Linux, and then you've got the three extensions. So you use the platform instance extension, the service instance extension, and the swap chain device extension. That's how things are split up. So it's as easy as 1, 2, 3. It is actually fairly straightforward. I am glossing over the stuff that Tobias showed. I'm glad he showed it. The key things that I'm not showing is how the synchronization works. That is the absolute key. If you look at the example he provided between present and acquire. So acquire gives you a semaphore that you can then use to make sure has the acquire actually happened, and so then when you presenting to a queue. So you must make sure that synchronization happens. But the black arrows here represent the steady state of your frame loop. So once you've created your swap chain, those are the 3 steps you go through every frame. So these lovely red arrows explain what happens when an event occurs that you need to deal with. So that's there are 2 types of events. So errors that can come up when you do an acquire, when you do a present. One is telling you your swap chain is suboptimal. And what that means is that your swap chain can still be used, you can still continue, but you may wish to recreate it because you can get some performance benefit. So let's say you're being scaled up and the scaling isn't optimal. If you recreated it, you can improve your performance. Service lost is it's gone. Don't try presenting anymore with this swap chain. You need to recreate it because either you disconnected the thing that you're presenting to, or the size is not compatible and we can't scale it. So that means you must start with a new swap chain. But there's a nice mechanism to create a new swap chain from your old swap chain, and the transition should be clean. And all of this belongs in the VK-KHR swap chain extension. So, on to Vulkan displays. So this is the mechanism to discover what displays are connected to to your Vulkan device outside of a Windows system. And a reminder that not all platforms support this. So this isn't supported on Android, for example, at the moment. May not be. It's a choice of whether this is desirable or not. Some platforms basically say you must go through the Windows system. That doesn't mean that an additional composition step happens every time. The compositor can be intelligent to know actually your full screen. I can bypass composition, but again, it's not available on all platforms. So the VKKHR display extension defines these two objects called the display and the display mode, as well as the display plane. So no, the display plane is not an object, sorry, it's a structure. And effectively, this shows the relationship between them. So a physical device will tell you what displays it can support and what combination of display modes and display planes can be used to create a Vulkan surface. And the additional thing that you can do is there's also ways to create custom display modes for displays that can support it. So different resolutions and different color mode settings. And what you get to eventually is creating the Vulkan surface we talked to earlier from a display plane, the representative display plane, sorry. And just again, a bit of clarity, a Vulkan display represents an actual display, whereas an EDL display is just a namespace representing a driver that's not a display. So, yes. Hope that's clear. Okay. So finally, in our set of extensions is the display swap chain extension. So this is the bolt-on to the swap chain extension that provides a couple of things. It adds the ability to provide additional information when you're doing the queue present, when you're submitting to your queue your presentable images. If you want a particular region within your swap chain image, and a particular region on your display to be targeted, as well as whether this notion of displays that can support persistent images, whether that's supported or not. And then it adds the ability to create this thing called a shared swap chain. And this is a structure that can take multiple swap chains at the same time. So it's an additional function that instead of submitting to one swap chain, you submit to multiple swap chains that can target separate displays. At the moment, it doesn't guarantee atomicity, i.e. you don't know that it's going to hit the displays at exactly the same time, but that's something that may be exposed in the future. Okay, so that's the overview. Hoping I'm sticking to time. Any questions? Anyone with the mic?
Thank you for the talk. What about cases where you want to share your swap chains between applications, such as in the Rift SDK? Between applications. So like in the Rift SDK where you talk to the VR server to get frame buffers to render into, and you render into them in your application, and then it is its own little presentation layer.
So you've got your, you described the setup, you've got the two.
So you talk to the VR server,
yeah,
and it's basically a compositor inside an application rather than inside the Windows system. So it composites the frames that you give it and then presents them on the Rift display.
So I think it depends how it exposes that. So I think one option is that it basically can do that as a layer, that it basically intercepts those commands before giving it an actual platform underneath. That's, I think, one way you could have that set up. There are no, I mean, the way like things are set up in Android, for example, is that the loader actually acts as the Windows System Integration implementation and has under the hood presentable images that are really just normal Vulkan images in each driver, and it basically does all the hooking up with service flinger. I think you could do similar thing with how Oculus SDK or others, but it's something that you need to look at in more detail.
We could ask them.
Huh?
They're in the working group. We could ask them.
Yeah. Definitely an interesting question.
Thank you.
Any other? All lines have been muted.
One thing about this, when you start with images, how do you actually provide synchronizing with the VC?
So at the moment, when you call qpresent, that doesn't in any way give you a timing guarantee from the presentation engine. So all that says is when qpresent returns on that queue, so it unblocks that queue, it means the GPU bit has handed it over, but you don't know at what point the presentation engine or display will pick that up. It'll be up to it to know. So if in FIFO mode, it basically waits until the next one is done before picking that up. There are questions about, we've had requests about looking at how we do timing of presentation. At the moment, it's effectively hidden like it is with EGL swap buffers, where you know you've sent it off, but you don't know when it's going to be picked up. Okay, in which case, thank you very much. I'll now hand over to Chris. So Chris is going to talk about the exciting stuff happening in compute in Vulkan and what future things it enables. Thank you.